This will be a reasonably short lecture. The purpose of this lecture is to introduce a topic that I call engineered materials, which is really a catch-all term for any type of material that we'll use in engineering. This can be chemists in the laboratory mixing test tubes and coming up with things like Teflon and different types of plastics and ceramics. Or maybe we take powders and liquids and mix them and get new properties. And then even more advanced, we have the metamaterials and photonic crystals. That'll be a big part of this class. So I like to lump all this together and label it engineered materials. The first thing I would like to do, which I think is really important, is to classify all of these engineered materials and to categorize a lot of what we talk about so we kind of understand what is meant and what is implied by these different titles. Now in this lecture, we will very briefly cover ordinary materials and then cover mixtures. The ordinary materials wasn't really ever part of this lecture. I added it. It's very brief. I just wrote it in the last 5 minutes. I do intend to beef that up, but it's useful because it explains some background concepts. But the main point of this lecture later on will be mixtures and different mixing rules. We mix two materials together, and the particle size is going to be extremely sub-wavelength, so there's nothing metamaterial or photonic crystal happening. But there's still a lot we can learn and some practices that we can understand to improve our material properties of mixtures. In one graphic here, I've tried to summarize and classify all of engineered materials. And really they're going from increasing complexity from left to right. We start with the ordinary materials. These are the pure things, pure copper, pure ceramic of some sort. Then we move up to mixtures. Maybe we have two different dielectric powders with two different dielectric constants. We mix them up, we stir it, and we get a dielectric constant somewhere in the middle. Those are mixtures. Those we'll talk about in this lecture. Next step in complexity are metamaterials. These are sub-wavelength enough that the wave is not scattering from site to site in the metamaterial lattice. However, it is large enough that somehow the wave is interacting with the individual elements to produce new and magical properties. Then even larger scale, when the periodicity is approaching the wavelength now the wave starts to scatter at all these different sites within the lattice, and we get this very complex arrangement of interference that leads again to some pretty neat and magical type of properties. Here, using a photonic band diagram, we're defining all of different regions of engineered materials. At the very, very low frequency, hard to see, but there's a sliver of gray down here. Extremely, extremely sub-wavelength. So the wavelength is much, much longer than what's happening. We call these ordinary materials and mixtures. So for ordinary materials, the wavelength is orders of magnitude larger than the atomic scale periodicity. And if we're mixing powders and nanoparticles, again, we'll assume that the wavelength is orders of magnitude greater than the particle size. A little bit larger than that, we have a region that we will call non-resonant metamaterials. The features in the lattice are too sub-wavelength to induce oscillating currents or anything else. It's more just it derives its properties from the distribution of power, but we can get some useful things to happen there. At a larger scale, now the elements are large enough that we can oscillate currents. Maybe they act like little antennas and little radiators, but it's still too small for the applied wave to interfere and scatter off of the different sites in the lattice. Then, above the resonant metamaterials is where we have the photonic crystal regime. And in fact, I guess a photonic crystal regime would go all the way up to extremely high frequencies. But at some point we get to such high frequency that it's not useful as a photonic crystal anymore. Here's just a visual interpretation of the size scale. So I drew a wave, and if we're looking at a tiny, tiny speck compared to the wavelength, that's the atomic scale. Those are the ordinary materials. Mixtures, just a little bit larger than the atomic scale. Metamaterials, maybe we're around 1/10 of a wavelength. And then photonic crystals, where we're around 1/2 of a wavelength in terms of our feature sizes. On to ordinary materials. Don't expect a lot out of this section. I just added it as a placeholder. As I come up with things to share, I will fill it in here. This was not originally part of this lecture, and really just added this within the last few minutes. But the first type of ordinary material are conductors. And this is where we have superconductors with approaching infinite conductivity. Graphene, almost as a superconductor, is receiving a lot of attention these days. And the more traditional ones, silver, copper, gold, and mercury. One thing interesting about mercury that I learned recently, way back in the old days, the Galileo telescope sort of days, they needed to make focusing mirrors and polish them very accurately. They didn't know how to do that. I learned that they would fill up buckets with mercury and spin those, and that those would form nice parabolic mirrors. I wish I could find more information on that, but I shared that story with you. Dielectrics, very common ones in electromagnetics is FR4. That's the plastic in a standard circuit board. Teflon, that tends to be the gold standard for dielectric constants. Anytime you want to calibrate measuring a dielectric constant, we'll put Teflon in there. Make sure we measure 2.1. Water is actually a dielectric, and it has a conductivity similar to wood. And we tend to think of water as conducting, and in fact, it doesn't. The only reason water does conduct is because it's not pure water. We'll put other things in it like salt. Salt water is a lot more conductive than just regular water, but deionized water is rather insulating. I also mentioned titanium dioxide, strontium titanate. These are commonly available in powder form and often used to backfill parts to provide a high dielectric constant. The claims are that they have very high dielectric constant in the order of 100 and 300. We really have yet to measure that in the lab to confirm that, but that's the claim. Magnetic materials, we have the diamagnetism, paramagnetism, ferromagnetism, and antiferromagnetism. We're really not going to talk about any of those in this class, but that is not to say that there's not a lot of wonderful stuff here with a lot of applications in electromagnetics. It's just not part of this course. Then we have the materials that are absorbers. Sometimes we want absorption. Salt water is a good absorber. The salt and the ions in the salt water make it very absorbing. Graphite. Think of these as black materials, even though we only see black at visible wavelengths, but if it's absorbing at other wavelengths, we can think of that as being very black and absorbing. Then we have our anisotropic materials, and from previous lectures, we know what causes a dielectric and magnetic response. We have charges, and they're bound. And if we displace those charges or tilt rotating charges, we're storing energy that can get re-released. And a little tiny re-radiated wave combines with the applied wave out of phase. We get an overall slowing response that we would either call the dielectric or magnetic response. Well, in some lattices, the charge is more easily displaced in one direction than the other, or the spinning charges are more easily tilted in one direction than the other. And it turns out that becomes anisotropic. When the charges are free to move in any direction the same way, we call that isotropic. When the charges are free to move in two directions and less or more free in the third direction, so in other words, two directions are the same, one direction is different, we call that uniaxial. And then if all three directions, the charges move differently, we call that biaxial. We also have what I call the bi-materials, bi-isotropic and bi-anisotropic. And what happens here for the bi-isotropic is we have modified constitutive relations. Normally, our constitutive relation for the electric field just contains D equals epsilon E. However, it is also possible that a magnetic field in a bi-isotropic material will induce a D field directly. And this constant would be a magnetoelectric coupling coefficient. And likewise, our other constitutive relation, the E field, can directly induce a B field. Then we have the Bi-Anisotropic materials, which are really the same constitutive relations. However, we just make all the constitutive parameters tensors, and we would call that Bi-Anisotropic. And then the last in the ordinary materials, we have our chiral materials, and these have the circularly polarized eigenstate. So this is where we get optical activity and Faraday rotation. And at the atomic scale, we actually see the atomic lattice as having some kind of spiral or chiral nature to that. And that has a profound effect on the electromagnetic waves. So that's it for the ordinary materials. I apologize for the very brief, rough lecture. It's meant as a placeholder. As I do come up with stuff that I want to share with you, I'll put it there. But anyway, it is what it is. And on to mixtures. This will be a much better part of this lecture. So what are mixtures? We're talking about mixing together two powders, for example. And we need the particles to be much, much, much less than a wavelength. Maybe it's 100th or 1,000th or 1,000,000th of a wavelength. If that's not the case, it starts to behave more like a metamaterial or photonic crystal. So the particle sizes need to be way, 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 way sub-wavelength. And when we mix two things, we really just get the average effect. Whereas one of the definitions of a metamaterial is that if we mix two different materials, we get properties that didn't exist in the two constituent materials, new and surprising and wonderful properties, because there's other physics that can be happening. Here, we're so sub-wavelength, we mix two materials, and we really just get an average of the properties. But what is that average? What do we get? And it turns out it depends on a lot of things. The shape of the particles has a very profound effect. The size of the particles, even the distribution of the size of the particles. The electromagnetic properties of the particles. Are the particles metal? Are they magnetic? Are they dielectric? Do they have loss? Also the statistics of the particle distribution. That can have a profound effect. And then the volume fill fraction of the materials. If we mix together one part of one material but 10 parts another, we would see that the overall material properties would be dominated by the second material. Unfortunately, we tend to mix the materials. We don't really have a good knowledge of the statistics of how they're distributed. So what we get rarely matches exactly what comes out of the mixing rules, but the mixing rules can certainly serve as a useful guide. Particle shapes. In terms of ease for manufacturing, making materials that are robust and just work well mechanically, we like spheres. Electromagnetically, spheres don't work so well. We get a very weak response from the spheres. And it turns out we want a very irregularly shaped particle. And in fact, flakes is one of the best particle shapes we can get electromagnetically. That perturbs the field more in the vicinity of the particle, and we get a stronger response. However, processing material with flakes isn't so good. They tend to agglomerate. If we're dispensing these through a nozzle, they can clog the nozzle. So spheres works better from a processing manufacturing perspective. Flakes works better from an electromagnetics perspective, and cylinders sort of fall somewhere in between spheres and flakes. So at the bottom of this page, I included a reference which discusses pretty well the effect of particle shape. And I won't really go through all the theory that's on this slide. Suffice to say that the shape of the particle has the ability to perturb the electric potential around that particle. The more oddly it's shaped, the more it perturbs the field. And in fact, the more that will dominate the mixture. So I have some pictures on the following slide that I think will explain that a little bit better, a little bit more intuitively. So on this slide, we have three different simulations that will hopefully give you an intuitive feel of really what's happening here. And we have three different shaped particles. Well, actually, we have the last two are the same shape in different orientations, so we'll extrapolate that to 3 dimensions. So our first particle is a sphere. And what we see are these little vectors. That's the electric field surrounding the particle. And without this sphere here, this electric field would just be straight from left to right. So somehow we have a plate here, maybe with a positive voltage, and a plate over here with a negative voltage. So if this particle weren't here, the electric field would just go straight from one plate to the other. However, when we introduce the particle, we see a bending of the electric fields in the vicinity of the particle. Now, the color in the background is not the magnitude of the electric field. What I did in the background is I colorized the deformation in the electric field. So the more the electric field is perturbed from that uniform case, the darker red the color. So what we can see is we have some deformations. That means it will affect the effective material properties because it's perturbing the electric field. That's the mechanism. Now if we had a cucumber-shaped particle where the big flat side is against the electric field, we see very little perturbation in the field. And what we can sort of conclude from this is that the electric field likes to be normal to the interfaces. So this big flat particle, the electric fields are essentially already normal to those interfaces. So there's very little perturbation. And in fact, if we had a bunch of these particles in a host, it really would have a very weak electromagnetic effect, weaker than the sphere. Now let's take the same particle and turn it 90 degrees. Well, in order for the fields to hit the interface at 90 degrees, they really have to bend in this case, and we can see a lot more perturbations on the field than we did even for the spherical case. So it turns out a particle in this orientation would have a strong electromagnetic effect and would dominate the material properties. Now, to extend this to 3 dimensions, what we can say is that spherical particles would have the least effect. And if we look at these 2 particles in 3 dimensions now, something like this would be a flat flake. Now here this flat flake is oriented the other way. So if it's pointing, if the oblong particle is pointing in parallel to the field, we get a lot more deformations. When it's perpendicular to the field, we get much less. Now if we think of a cylinder, it in fact has 2 dimensions that would have very little perturbations. The 3rd dimension would have a lot. A flake particle, 2 of its dimensions would give us great deformation to the field, 1 wouldn't. So the flake overall gives us more deformations, more perturbations to the field, and in fact gives us the strongest electromagnetic response. So remember, in these figures, the color is not conveying the strength of the electric field, it's conveying how much it's changed from the uniform field going from left to right. Particle size. If we could zoom in on a particle, what happens very often is that at the inside of the particle we get a nice pure crystal. However, on the outside it's imperfect and we get a much less pure crystal. Well, if the pure crystal had some high dielectric constant, something with defects and is less pure will very likely have a much lower dielectric constant. So if we take this into consideration with the size of the particle, if we have a large particle, this region of the imperfect crystal becomes much less significant, and in fact the overall dielectric constant really would be dominated by the dielectric constant of the pure crystal. With a smaller particle, now there's a much higher percentage of the volume that is this imperfect crystal, and in which case the overall dielectric constant will go down because now the outer imperfect crystal is more dominant. So from an electromagnetics perspective, we really want larger particles. Those will work electromagnetically better. However, on the manufacturing side, the larger particles limit how small of features we can realize, mechanisms of how we dispense them or manufacture with them. So from a manufacturing process perspective, we want very small particles. But here's one problem that small particles can give us. Intuitively, we know if we're loading a host with some kind of powder, the more powder we can get in there per unit volume, the more that powder can dominate the electromagnetic properties. So interestingly, independent of particle size, as long as they have the same particle shape, the fill fraction will be the same. We can have large particles and small particles. and they will have the same fill fraction. Why is that? Because the small particles is just a scaled version of the big particles. We're still filling the same percent volume, and electromagnetically they will behave the same. Well, what if we mix the two? Well, if we just had the large particles, we'd have the same fill fraction we have over here. However, when we incorporate the small particles, we're starting to fill the gaps. So in fact, mixing particles of different sizes helps us achieve a higher fill fraction of the particles and then stronger properties. I don't think it's really known where exactly this is optimal, but the rule of thumb in the industry is about a 10-to-1 ratio. If we can mix particles where the small ones are about 10 times smaller than the large ones, we will get this higher fill fraction and we can dominate the electromagnetic properties even more. Now let's think about the particle spacing. If we have a very, very low fill fraction, so there's really not much filler in the host, and so I visualize it this way, where we have very sparsely spaced particles, they are too far away for there to be some kind of inter-electromagnetic phenomenon that couples the two. So they're completely independent. They're far enough away that they're independent. And so what we see, the effective dielectric constant really just increases linearly as we increase the fill fraction. And that makes sense. They're not interacting with each other. However, at some critical point that we'll call the elbow, the particles are now spaced close enough that there's this mutual coupling, and one particle is helping to perturb the field around the other. A different set of physics takes over. And in fact, the effect on the dielectric constant, or the average material properties, really takes off exponentially. And we get much more, the filler will dominate the electromagnetic properties now that there's this enhanced interaction. So I'm visualizing a mixture this way, where the particles are so close, they're interacting. And so if we want to dominate the electromagnetic properties, we tend to favor these higher fill fractions because there's increased interaction between the particles and an enhanced effect on the overall electromagnetic properties. So if we mix two materials with an epsilon 1 and an epsilon 2, no matter what the particle sizes, no matter what the statistics of the distribution, no matter what, we can define an absolute minimum and an absolute maximum of that mixture can achieve, and we call those the Wiener bounds. So if we have a two-component system, which is certainly the most common, here are our bounding dielectric constants. So we have a mixture of something with epsilon 1 and epsilon 2. F will be the fill fraction. This is an equation that will give us the minimum possible dielectric constant and the maximum possible dielectric constant. And we can also generalize this to multiple component systems if we're mixing together 3, 4, 5 different things. But if we plot these Wiener bounds, what we see is the maximum possible, essentially just linearly tapering, and then the minimum possible has this elbow action. When we mix two different things, it has to fall within this gray area somewhere. So these Wiener bounds are very good in that we don't have to know anything about how the particles are actually distributed or the shape of the particles or anything like that. We can immediately define minimum and maximum. So the reference I have at the lower right here provides mixing rules. So in other words, we mix two things, what do we get? It provides mixing rules, but it differentiates between two different things. It differentiates between the particle shape, spherical, cylindrical, or flake, and also between low fill fraction and high fill fraction. Remember, the low fill fraction is where the particles are so far apart they're not interacting, whereas when we go to a high fill fraction, the particles are close enough, they're perturbing each other's fields, and we get even a greater, more enhanced effect. So plotting all this, including the Wiener bounds, so this thick red line is the upper Wiener bound, this thick blue line is the lower Wiener bound. The gray area are the only physically possible things to realize with these two mixtures, and we can compare what happens. Well, the spherical particles are these purple lines here. Notice they're the lowest possible lines. Now, if we look at the low fill fraction line, the dashed line, that's this one. Once we get to 30, 40, 50%, we really should ignore this line. It doesn't have a lot of physical meaning. And likewise for low fill fraction, we really should be ignoring the solid line. But I plotted them over the whole thing just for completeness so we could see that. But anyway, for low fill fractions, we definitely see really almost nothing happening for spherical particles. However, when we get to larger fill fractions, there's an elbow that happens. And in this case, somewhere around 30%, and it really takes off. But spheres is the lowest. Cylindrical shaped particles, those are the green lines. Well, these fall between the flakes and the spheres, and they're somewhere in between. But definitely the best in terms of achieving strong electromagnetic properties are flake particles. So these are the orange lines, and we see these here. So if we are mixing some kind of powder, let's say, into a resin, and we want really a strong electromagnetic response, we want those particles to be dominating the electromagnetic properties, we want flake particles. And according to this, we also want high fill fractions. There's other mixing rules. These are the exponential mixing rules. I don't see them being any better or any worse than other mixing rules. It gives us a different set of degrees of freedom if we're doing curve fitting or empirical fits to data. But there's also the exponential mixing rules. And logarithmic mixing rules. I tend to stick with the standard mixing rules. I have not actually ever used the exponential or logarithmic mixing rules, but they're out there, and I want you to see them and be familiar with them. One of the more famous mixing rules is called the Maxwell-Garnett and Maxwell-Garnett effective media. This is the low fill fraction. The particles are spaced far enough apart, there's no mutual interaction, and we can estimate what the effective properties are. So we mix two things. We have something that has a dielectric constant of 1, that'll be our particles. We have a background or host that has epsilon 2 dielectric constant, and then F will be the fill fraction of the loading material, or epsilon 1. If we do that, we get an overall effective dielectric constant, epsilon mg. Now, in terms of accuracy, these fall right in with the spherical, cylindrical, flake mixing rules we had a few slides ago. This one is more famous. There's a lot of folks that talk about Maxwell-Garnett media, and it still is a really good approximation. Then we have the Bruggeman effective media. This is the sort of the same thing now, but for higher fill fraction. But we still have one of the particles being epsilon 1, the host or maybe a second particle being epsilon 2, and F being the volume fill fraction of epsilon 1, and then the overall effective dielectric constant of this mixture is the epsilon sub b. And so this would be a Bruggeman effective material. So one thing that's useful is to solve these equations for the effective material properties, and here's the equations for you so you don't have to do that. So if we were to calculate the effective Maxwell-Garnett dielectric constant, we'd first calculate this intermediate parameter A, which is just in terms of epsilon 1 and 2, and then we calculate the effective dielectric constant using the Maxwell-Garnett rule. Bruggeman, here's the solution. We calculate 3 intermediate parameters that are only a function of epsilon 1 and 2, and then we put them together and solve for the Bruggeman. If we want to compare Maxwell-Garnett to the Bruggeman, here are the plots for different mixtures. In the upper left, we're mixing two things with a dielectric constant of 1 and 2. So for very low dielectric constants, very similar dielectric constants, there's not really a lot of difference between the Maxwell-Garnett and Bruggeman. Here we go to really high dielectric contrast, and we see a very large difference between the Maxwell-Garnett and the Bruggeman. Notice the Maxwell-Garnett is the lowest possible value, and the Bruggeman is the highest. Because remember, the Maxwell-Garnett assumes dilute media, so really out here, I wouldn't even say it's valid to use it out here. Whereas Bruggeman, we're more interested in this region. But we can see the difference, what the two models would give us. If we have very high dielectric constant with moderate contrast, we see very little difference between Maxwell-Garnett and Bruggeman. If we have high dielectric constant and high contrast, we see a little bit of difference. So really we see the biggest difference when one of them is a very, very low dielectric constant and the other one's a very, very high dielectric constant. Otherwise, there's not a real big difference between the two models. And I'll leave you with, there's also a 3-component Maxwell-Garnett, 3-component Bruggeman. If you looked hard enough, maybe you'll find 4 or 5-component, whatever. So here's the reference and the equations for 3-component models.